Okay, I'm going to start off today with some questions over some problems that were asked by students. First one is, what is the limit? That looks terrible. What is the limit as x approaches infinity of cosine x? Well, first of all, let's take a look at what the cosine function looks like graphically. So we know cosine actually starts up here at 1, here's -1, and the cosine does something like this, and it continues to do that forever, and it goes the other direction, does the same sort of thing. Now, what we want to know is what is happening as this thing approaches infinity. So we're trying to figure out, as we move our x values out the left side, where is this thing going? And as you can see, it's not going to any particular number. It's oscillating back and forth between -1 and 1. And because of that, because the limit is not approaching something specific, a specific number, we will say that this limit does not exist. DNE does not exist. So the answer to this one we get by just our knowledge of what the graph of this looks like. Let's look at another example. What is the limit as x approaches 2 pi with a little negative up there, which means from the left-hand side of x cosecant x? Well, we could start looking at, what does cosecant look like and then try and figure out what's happening if we multiply by x. Or what we can do is we can rewrite this using our knowledge of what cosecant is. Cosecant, we know, is 1 over sine. So this is x times 1 over sine x. But that is the same as limit x approaches 2 pi from the left of just x over sine x. Now let's just do a quick little plug-in. Let's just plug 2 pi in and see what we get. We plug 2 pi in on the top, we get 2 pi. If we plug 2 pi in the bottom, sine of 2 pi is going to be 0. So what we're getting here is we're getting a fixed number on top divided by something that is approaching 0. And so anytime we get a fixed number on top divided by something that's going to 0, we know that it's going to be one of three things. The answer is either going to be positive infinity, negative infinity, or possibly the limit does not exist. So all I have to figure out is whether or not the top is going to a fixed positive number and whether or not we're approaching 0 from negative values or positive. So that says plus or minus. So let's think about this. On a number line, right, we are approaching the value of 2 pi. This is our x value. We are approaching it from the left, so we're coming in this side. We're going to be values that are a little bit smaller than 2 pi. And if I now look at, approaching values to the left of 2 pi, up here, this top part, this fixed part, is obviously going to be a positive number because as we approach 2 pi is positive. As we come in from the left side, it's positive still. So we know the fixed number on top is positive, and we also know that the bottom one is approaching 0, but is it approaching it from positive or negative numbers? So maybe we can look at the sine function. So what I'm doing is I'm isolating all my attention here on what the sine function is doing. We know sine looks like this. And we know that at 2 pi, we're here at 0, which is what we expected, right? We knew that we were going to get 0 there when we plugged 2 pi in. But as we approach 2 pi from the left side, we're actually moving along the graph to the left of 2 pi. As you can see, we're coming into 0, but we're coming in from below the x-axis, which means that the sine of that function, sine of all of those little values here are going to be negative values because they're below the x-axis. So I know that I'm approaching 0 down here, again, but I know that these are little negative numbers. So what I have is on top, I have a fixed positive number, and it's being divided by something that is approaching 0, but approaching 0 from the left. In other words, approaching 0 with negative numbers. So I'm going to put a little negative right there. So what I can conclude from all of this is that my answer must be negative infinity, because I have a positive number divided by some small negative number. So therefore, we get negative infinity. So the answer, okay, the answer to this is negative infinity. Well, I hope that makes sense. Okay, let's take a look at another one. This one's kind of tricky. Limit x approaches infinity of, in parentheses, square root 9x squared plus x minus 3x. Okay, real quick, let's just plug things in. If I plug infinity in right here, we get infinity squared, which is infinity, times 9 is still infinity. So I've got like an infinity there. Plus, I plug in infinity again, I get infinity. Then I take the square root. Square root of 2 infinity is still infinity. So this is becoming infinite. But then I'm subtracting 3 times infinity, which is still infinity. So I get infinity minus infinity. Infinity minus infinity is not 0. What it's saying is one thing's getting really big, the other thing's getting really big, and there's that tug of war happening. Who's going to win this battle? You know, maybe one of them is going to win, you know, get bigger faster than the other one, or maybe they're going to compromise and something else is going to happen. So what we're going to do is kind of a trick that we have done before in the past. Because we have square roots involved here, and we have 2 terms. All right, there's our 2 terms. We're going to come in here and we're going to multiply by 1. But the one that I'm going to choose is going to be very clever. I'm going to choose the conjugate of what I see there. So it's the same thing here. I use a plus instead of a minus, and then 3. And then whatever I did on top, I have to do on the bottom, because that's a 1. And just imagine that this is all over 1. And so now what I'll do is I'll go ahead and do like a FOIL. I multiply these 2 together. Keep the limit here. X is going to infinity. Multiply those 2 together. Since they're identical and they're both square roots, you're basically squaring a square root. So the square root goes away. Get 9x squared plus x. Now we know, because these are conjugates, when I do this one and this one, they're going to be the exact same terms. They're going to be off. They're going to differ by a sign, so they're going to cancel each other out. And then this times this, that last one, negative 3 times positive 3, gives us negative 9. And then all over on the bottom, oh, sorry, I messed up. I just noticed I forgot the x here. Oops, this x right there. And I need that again. You're probably going, what the hell? Okay, there, 3x, 3x. When I multiplied that last one over here, I should have got 9x squared. Okay, sorry about that. And then on the bottom, we have just 1 times this, which is the same thing. And I'm just going to leave it just like that. Square root 9x squared plus x plus 3x. And then notice what happens up here on top. The 9x squared minus 9x squared, they go away. So here's where I am now. I'm at, still have the limit because I have not let x go to infinity yet. Now I have something like this, x over square root 9x squared plus x plus 3x. Now, at this point, I have letting x go to infinity again. I'm going to see what I've got. Up on top, I've got infinity, right? X goes to infinity. Over here, we've got infinity again, right? This thing is infinity, and then plus another infinity, and infinity plus infinity is infinity. So now what we get is infinity divided by infinity. See, earlier we had infinity minus infinity. We really didn't know what that turned out to be. We said it wasn't 0. And then now we've converted this whole problem into infinity divided by infinity instead. Well, this is actually a good thing, because we have a little trick that we can use whenever we have infinity over infinity. I'll keep that there. And what we try and do is we try and come in here with something very, very tricky in order to get some of these to go to 0. So watch what I do first, then I'll explain. What I'm going to do is I'm going to multiply the top and the bottom by 1 over x. Now I'll explain why I did this in just a second. On the bottom I have that entire denominator, 9x squared plus x, and then plus 3x. Now, what's going to happen here is when I distribute, of course, this to this, that just becomes a 1. So I have a 1 on top. But on the bottom, when I multiply 1 over x times that square root, let me do that down here just to show you. What we have is, remember, anytime you try and push something into a square root, it gets squared as it goes in. And therefore, this is going to turn into a 1 over x squared times, because it got squared when it went in, times whatever was there. And now I'll distribute that in. And I get square root, let's see, I'll get 9x squared over x squared plus x over x squared. This is just square root of 9 plus 1 over x, because these things kind of reduce down. So that multiplication, this one right here, this to here, goes in there, gets squared, and turns out to be this. So I'm going to put that down here. And then when I go and do 1 over x times 3x, the x's cancel. So all I get is plus 3 on here. And now let x go to infinity. Things are going to be wonderful. X goes to infinity. 1 divided by something that's becoming infinite, we've already talked about, this is going to go to 0, right, when I take the limit. So what's left then? So now I'm taking the limit, so I'm not going to write it anymore. The numerator is 1. Nothing changed. The denominator, however, this term vanishes, right, goes to 0. So I'm left with square root of 9. Square root of 9 is 3. Plus, we're left with that 3 out there. So we get 1 over 6. Wow, okay. So what we're saying is that as x gets larger and larger, these two infinities are fighting each other out, fighting each other, seeing who's getting bigger faster. Well, what happens is that the difference between those two terms is getting closer and closer and closer to 1 divided by 6. The further out you go, the bigger your x values, the closer and closer you'll get to the value of 1/6. So a couple of tricks in that problem. I mean, you had to come in with a conjugate. Once you did that, you had to come in here and realize that you could bring in this clever 1 over x over 1 over x, and then good things happen. Now, I will say the reason why I use 1 over x is because I realized I had an x squared here. And to make that x squared go away, I knew something was going to have to go inside this and cancel it. So I needed to make sure I had an x squared on the bottom to cancel it out. Well, I know that to get an x squared on the bottom, because it's going to be forced in the root, it's going to get squared on its way in. So I used a 1 over x. So you'll just have to practice with those, see if you can kind of catch on to that. Okay, let me take a quick little break here. Okay, let's continue here. All right, so we're going to talk a little bit about now the equation of the tangent line to some graph or some function at a particular value. So this just means, again, you have a graph, f, and we pick some point, x equals a, up on this graph, boom, right there. And what we want to know is not what is the slope of this tangent line. We don't want to know what the slope of that is. We can find that. What we want to know is what's the equation of this line. So let's just keep in mind that you can find the equation of the line using this formula, y minus y1 equals m times x minus x1. This is called your point slope formula of a line. So it says if you know a point, right, which in this case the point we know is the point x1, y1, and we know the slope of the line, which in our case the slope is actually going to be the limit as x approaches a of f of x, minus f of a over x minus a. We talked about that last time. So that's like our derivative. So we can find that slope. Okay, so we can find the slope of this line up here by using this limit. And then all we need to do is know the actual x and y coordinate of that point, and we can come up with the equation of the line. So let's go ahead and do an example. This is actually page 81, number 4. So it says find the equation of the line tangent to y equals x cubed minus 3x plus 1 at the point 2, 3. All right, so first of all, we already know what x1 and y1 are. They've already given that to us, so we're real happy about that. And all we need now is to find that slope. The slope of that tangent line is going to be equal to the limit as x approaches a, f of x minus f of a, all over x minus a. Now here in this problem, we know what a is, right? A is the x value. And we also know the function. We're just going to replace the y here with f of x. So let's get these pieces here. F of x. All right, f of x is just going to be this. All right. Then we're going to need f of a. So f of a is going to be what we get when we plug 2 into this function. So let me do that over here on the side. What is f of 2? Well, f of 2 is 2 cubed minus 3 times 2 plus 1, which is 8 minus 6 plus 1, which gives me 1. Okay? Oh, sorry, 1, 3. Duh, this is 2 plus 1, 3. All right, so I kind of know what the pieces are here already, right? This is 3, and then this piece is that. And then down here, that's going to be replaced with a 2. So let me rewrite this. The slope of my tangent line should be the limit as x approaches, oh yeah, this one I forgot to mention, that a is 2, of f of x, which is x cubed minus 3x plus 1, and then minus, that's right here, minus what we just got when we plugged a in, or we plugged 2 into the function. So that's our 3. All over x minus 2. All right, let's just clean that up a little bit on top there. Again, not taking the limit yet. I'm not going to let x go to 2 yet. I should get x cubed minus 3x minus 2 over x minus 2. Now, right now, if you try and let x go to 2, what you're going to get on top is 0, and what you're going to get on bottom is 0. And this is really the bad situation. Well, it's a good situation for calculus students, but it's a bad situation overall. So what we're going to do now is we're going to try to somehow algebraically manipulate this so we can get something to cancel, so we no longer have 0 over 0. So we look at what we can do here. Look at the numerator. It almost looks like a quadratic, right? Because 3 terms, right? We've got minus 3x and minus 2, except that this is not an x squared. So we can't just factor that, you know, like we do a quadratic. So we're going to have to do something else with this. So let me grab this for a second. Well, you know what? I'm going to grab the whole thing. There we go. Grab this whole thing. Take it to the next page with me. Oh, no. Get a new page. All right, so let's take just this numerator for a second. Let's see if you recall or remember from your days in college algebra how you can factor something like x cubed minus 3x minus 2. So in case you have forgotten, we have a way of factoring, and it involves using what's called synthetic division. And if you don't remember how to do this, please look that up and review it. But what basically it turns out to be in this case is you look at you look at two numbers. You look at the number in front of your highest power of x. You look at the number of the constant by itself, -2. And you're supposed to create this list of possible numbers from it. And again, I'm not going to show you exactly how to do that, but in this case, we would get 1 and 2. That's basically turns out to be all the factors of 2. So you could have 1 times -2. You could have -1 times +2. These things multiply to give you -2, which is here. So please look up synthetic division if you've forgotten this. Now what you do in synthetic division is you do this upside down box, and you put in the coefficients of the polynomial you're trying to factor. So I'm going to put in the 1 that's in front of x cubed. I do not have an x squared, so I have to represent it with a 0. Then I put a -3, then I put a -2. Okay, and then at this point, I start using these and trying to do synthetic division until I get a remainder down here of 0. So let me try +1 first. Synthetic division, I bring the 1 down, multiply 1 times 1 is 1. Add down, we get 1. 1 times 1 is 1. Add down, we get -2. Multiply -2, this is -4. That is not 0 in the remainder, so that didn't work. So now I try it again, and this time I try another number. So let me try here instead of +1, -1. 1 comes down, multiply, -1, add down, multiply, +1, this is -2, +2, and when you add down, you get 0. So yes, that does work. Now what this tells us is that the original polynomial factors, we're using the 1, like a 1 in front of x squared, minus like a 1 in front of x, and then this -2, that this is part of it, and the other part comes from this number, x plus 1. So basically, using synthetic division, I can guarantee you that the original polynomial, that numerator up there, it's going to be hard to see, that right there turns into this, right? So what I can do now is rewrite this. Okay, limit x approaches 2. I have the top is x plus 1 times x squared minus x minus 2, and then over x minus 2. Now at this point, I haven't really done anything that's going to help unless I realize that this is now a quadratic and that can factor even more. So assuming you can factor quadratics quite easily, you'd realize that that factors to be x minus 2 times x plus 1 all over x minus 2. And hopefully you see what happens here. We have a common factor, and those can cancel. So now what we're left with is just limit x approaches 2 of x plus 1 times x plus 1, which is x plus 1 squared. And now finally I'll let x approach 2. If x approaches 2, I get 2 plus 1 is 3. 3 squared is 9. So we get 9. Pretty interesting there, huh? Pretty interesting. Okay, let's now look at this same problem. I want you to see that there is a different way to do this. We could use the other definition of the tangent line to do the exact same problem. So, oh wait, hold on. That's just my slope. Oops, I need to get my equation. I'm just blanking today. Remember, I need my equation and my tangent line. So this is my point slope formula. Okay, we said earlier that the point that was given to us was the point 2, 3. This is my x1, this is my y1. So I have y minus 3 equals the slope, which we just found to be 9, times x minus 2. So that's the equation. I can clean this up a little bit. Y minus 3 equals 9x minus 18. And then just go ahead and add 3 to both sides. And you get 9x minus 15. And that is it. Now, that was the way we did this, okay, required synthetic division, which was a real pain in the butt, right? But that's also because we used this definition here of the slope of the tangent line. We also have the alternative definition. And I want you to see how this problem would work out if you use the alternative definition. So remember our two definitions, limit x approaches a, f of x minus f of a all over x minus a. That's option 1. The other option, limit h approaches 0, f of x, or a plus h, sorry, minus f of a all over h. Okay, we are going to do this one now, all right, to get that slope. So remember what our function was. The function that was given to us was x cubed minus 3x. I forgot what it was, minus 3x plus 1. And to figure out this, what we're going to need to do is figure out what f of a plus h is. Well, for us in this problem, remember a is 2, so we actually want to know what f of 2 plus h is minus f of 2 all over h. F of 2 plus h, the way to get that is to plug 2 plus h into the function. So replace all your x's with 2 plus h. So cube that minus 3 times 2 plus h, and then in parentheses plus 1. All right, I'm going to cube this. That means I'm going to have to multiply this times itself 3 times. I'm just going to do that. 8 plus 4h plus 2h squared plus h cubed. All right, so I'm doing that based on a little bit of knowledge of polynomial expansions. So don't worry yourself too much about that. I mean, you would have to do it on the side, 2 plus h times 2 plus h times 2 plus h. We could have a whole class on fun stuff on this, how to expand those easily, but I'll skip that for now. Then I have here distribute through, let's see, minus 6 minus 3h, and then plus 1. Let's collect like terms together here. Let me see, I've got h cubed, put this in descending order, plus 2h squared, plus, you know what? I got a problem. Hold on. Hold on. I expanded that wrong. Geez, it's just one of those days. Okay, 8 plus 12h, plus I forgot the 3 that I have to factor those by. Okay, so this becomes what I just wrote, and then minus 6, and then minus 3h plus 1. All right, that's what that is. And then let me collect my like terms together now. So I have h cubed plus 6h squared. Let's see, how many h's do I have? 12, and then take away 3, so 9h. And then, let's see, 8 minus 6 is 2, plus 1 is 3. So I have 3. All right, so what I know now is this top left corner is going to be all of this. The top right corner is f of 2. We already know f of 2 came out to be 3. We did that in the previous problem. Or you can just plug it in right here. Plug 2 in. So let me take this now. I'm ready to take that and try and see what I get. All right, limit h approaches 0 of the top left, which was h cubed plus 6h squared plus 9h plus 3. Then I subtract from that f of 2, which we know is 3. And then I divide by h. These 3's cancel, which is extremely convenient, because now everything has an h in it in the numerator. So I can factor an h out, be left with h squared plus 6h plus 9, divide that by h, and you see, voila, we get our cancellation. And now you can let h go to 0 because you're not going to have division by 0. So when h goes to 0 now, this will vanish, and the only thing left will be a 9. And so the slope of the tangent line is 9 at that point. And then you go on and proceed to get the rest of the equation. So I think this is a much cleaner way of getting that slope of the tangent line using the second definition. All right, let's do another example. Same exact thing. This is number 6 off page 81. Gives you y equals 2x plus 1 over x plus 2. And we're looking at the point 1, 1. So we already know our x1, y1 again. And so what we need to do is get the slope. We get to choose our definition of the tangent line, the slope of tangent line. So I'm going to go, let me use this one, limit. Here x approaches a, which is 1, of f of x minus f of a, which is 1, all over x minus a, which is 1. So let's use that one. Let's just see where it takes us. So I get limit x approaches 1 of f of x. That's my top left corner here, f of x. What is f of x? Well, it's this. So I'm going to write that whole thing down as a fraction. 2x plus 1 over x plus 2 minus what we get when we plug 1 in. Well, we already know what happens when we plug in 1, right? We should get 1 because that point lives on that graph. But you could verify it. Just plug it in. Plug in 1, you get 3 over 3. So you get 1. So it's all of that minus 1. All of this over x minus 1. Okay, at this point, if you try to let x be 1, what you're going to get is 0 over 0. So again, we're going to need some sort of algebra to try and work this out. So here's the algebra that I'm going to employ here. I'm going to, because I have a fraction up here, and then a bigger fraction, so this complex fraction, I'm going to look in the numerator, I'm going to get a common denominator. So what I mean by that is I'm going to try and get this 1 to be rewritten as 1 over 1, and then I'm trying to get the same denominators on the bottom here. So what I need to do is make an x plus 2 appear down here. The only way to make an x plus 2 appear down here is to multiply the bottom and the top by x plus 2. That's still a 1, but I've rewritten it so I can combine these two fractions together. So what I have now, limit x approaches 1, is I'm going to have this top. I'm going to subtract this, so be careful that negative sign will carry through. So I'll have 2x plus 1. I subtract x, I subtract 2. All of that over the common denominator, which was x plus 2. All of that over the original denominator there, x minus 1. And if things work out nicely here, we should get something to cancel. Let's see. We have 2x take away x, that's x. We have 1 take away 2. That's going to be negative 1. So we have x minus 1 over the common denominator, x plus 2, over the original denominator, x minus 1. And now I have a fraction over a fraction because I can look at that x minus 1 as being over 1. And what I can do is rewrite a fraction over a fraction, or a fraction divided by a fraction, as multiplication of the reciprocal. So I'm just going to take the fraction on the bottom and flip it and bring it up as a multiplication. So this got flipped and came up. And now you can see quite a nice thing happens. Those cancel. So I'm left with limit x approaches 1 of 1 over x plus 2. And now let x go to 1, you get 1 over 3. So this limit is 1 over 3, which means the slope of my tangent line is 1 over 3. So now I can rewrite or use that formula, y minus y1 equals m times x minus x1. So y minus y1 was 1, my slope was 1/3, and then x minus my x1, which was 1. Distribute. This is not absolutely necessary, but I encourage you to just take this all the way and try and solve it for y. I'm going to add 1 to both sides. 1/3, negative 1/3 plus 1 is 2/3. There we go. That is the equation of your tangent line. I'm going to do one more and take a little break. By the way, if you're wondering why I'm taking breaks and stuff, it's because this video originally, when I made it in class, the audio didn't pick up, so I had to redo it at home. So that's what I'm doing right now. Okay, so we want to find the slope of the tangent line to this graph at the point, or at, I should say, x equals a. So this time they don't give us a point, right? They don't say like 2, 5, or something like that. They don't give us anything like that. They just say, hey, look, at a, what's the slope of the line here? So they're not asking for the equation. They want find slope. So find slope tangent line. All right, well, we have one of two definitions that we can use. I'm going to go ahead and use this definition. Slope tangent line equals limit x approaches a, f of x minus f of a over x minus a. So this should give us the slope of the tangent line at a. Does that make sense? And look, we want to know what's happening when x is a. Well, that's what this formula tells us. It gives us a general answer for any value of a. So if a was 2, we just replace that with 2, but we're not going to. We're just going to leave it. So let's just try and figure out what this turns out to be here. We have limit x approaches a of f of x. Now, f of x is just this. So f of x is 1 over square root of x minus f of a. Well, what happens when you plug a in right there for x? You just get 1 over square root of a all over x minus a. Ooh, this does not look good. If we right now let x become a, right, so let that x and that x become a, we're going to get basically 0 over 0. So nothing works there. At that point, that didn't help. So we have a fraction on top over this bigger fraction. So like I just said, we're going to try and get a common denominator. So to get a common denominator, I'm going to need a square root of x here and a square root of x here, and then a square root of a here and a square root of a here. That way they both have the exact same denominators. So let's go ahead and do that. So we're multiplying by 1, right? This is a 1 right here. This is a 1 right here. Root a times 1 gives me root a. I need to rewrite this limit. Give myself a little more room. Okay, root a over root, I'm just going to say ax. I can put them together. And then, let's see, 1 times root x is root x over root ax again. Then all of that divided by my common denominator. Now that they have the same denominator, or sorry, I said common denominator, all divided by the original denominator there, x minus a. But since these two have a common denominator now, I can put them together, which just means I take this, subtract this. And let's see if that gets us anywhere. Limit x approaches a of root a minus root x over root ax all over x minus a. Unfortunately, nothing looks like it's going to cancel here, right? We were hoping that maybe this would cancel out with something up here, but it doesn't. So now here I come again with my tricky algebra inside of calculus here. I'm going to multiply by 1 here, very special 1. I'm going to choose to bring in the conjugate of the numerator up there. Now, conjugate, the reason I'm thinking conjugate is because conjugate, when you do it, it gets rid of roots. So whatever I do on top, I have to do on the bottom. So notice I've inserted a 1 here. That's a 1. All right, so I haven't changed the problem. And I'm going to multiply this through, so I'm going to do like a foiling up here. And let's go ahead and see where that gets us. So limit x approaches a. Let's see, that first multiplication, the roots cancel out, you just get a. We know that the middle two are going to cancel each other out, so I don't have to worry about that. My last multiplication, negative root x times positive root x. Negative times positive is negative, and the roots will kill each other off. Now, below that, I had that root ax there, and I had to multiply that times that conjugate, which I'm not going to do. I'm just going to leave it written like this. I'm not going to distribute that all over the bottom, which is x minus a. And look at this. We have a minus x up here and x minus a down here. And those are almost the same. They're just off by a sign. So remember, the bottom here is a fraction. So if we look at this division bar, we have a fraction on top divided by a fraction on the bottom. And so we can flip it and let it become multiplication of the reciprocal. So let me do that. Limit x minus a, or x approaches a, of a minus x over that root ax times root a plus root x. Now I'm flipping the denominator and bringing it up here. It's 1 over, And then instead of writing x minus a, I'm going to factor out a negative 1 or negative and make it instead a minus x. And now, hopefully you see that these two are the same and they cancel. But we still have that negative there, so we have to keep count of that. All right, so here's where I am. I have limit x approaches a. That negative that was down here, I'm just going to pop it to the top, make it a negative 1, over root ax, and then in that parentheses, root a plus root x. And now I'm ready to let all my x's become a's. Nothing changes up here. Notice the limit's gone now. I have root a times a, and then I have square root a plus this is now square root a. So I have negative 1 over, this right here is a squared, but then square root, so you should just get a. And then times root a plus root a is 2 root a, so 2 root a. And this, my friends, is the slope of the tangent line. Now you could write that a different way because remember, you could write that denominator like this, or you could write that as square root of a is the same as a to the 1/2. So you could write that as a to the 3/2 by using the properties of exponents that you would add the exponents. 1 plus a half is 3/2. So that denominator could be this, right? That could be how you rewrite that. So that's it. That is the slope of the tangent line at A. So now if someone says, hey, what's the slope of the tangent line of this graph at 4? You would just come over here and you just plug 4 in right here. If they said, oh, what's the slope of the tangent line here at 9? You just plug 9 in. So for pretty much any positive value of A, we could figure this out. All right. Let's see if there's anything else here. Let me take a quick break. Okay, back to business here. I want to take this result here and just show you a couple of ways we could use this. Remembering that the whole idea here was that if we have a graph here and we want to find the tangent line at any value of x, we can do it in general and get a general answer. And then if someone says, find the equation of the tangent line to y equals 1 over the square root of x at, let's say, 4 1/2. So that's a point on the graph. Then using what we just figured out, we know that the slope of the tangent line at any point x equals a is negative 1 over 2a root a. So if here a is 4, we plug in 4 here, you get negative 1 over, let's see, 2 times 4 is 8 times the square root of 4, which is 2, so we get negative 1/16. So we know we have a negative slope there. So the equation of tangent line would be y minus y1, just 1/2, equals the slope, negative 1/16, x minus x1, x minus 4. And then we could simplify, we could try and get y by itself, but that's the equation. So, and I could do that for any point. So finding a general solution is actually pretty valuable because it speeds up the process if you're trying to find equations of several tangent lines. All right, let's take a look at another example. How about using now this whole concept of the general derivative? So if we have this, and you're asked to find this. So this is f prime of a, which means the slope of the tangent line at a, okay, at x equals a. So we can use two definitions to do this. I'm going to use the first definition, or the one that we've been using, limit, whoa, lost my drawing there. X approaches a, f of x minus f of a over x minus a. So this is going to be equal to the limit as x approaches a of f of x, that's my top left there, it's 4 over square root 1 minus x, minus f of a. So what would happen if I replace that x with a? I would get this all over x minus a. And this just doesn't look very fun because we have a complex fraction. So just like we have been doing before, what we need to do is we need to make a common denominator. So I'm going to multiply the top here by root 1 minus x, bottom root 1 minus x. Over here I'm going to multiply top and bottom by root 1 minus a, and then over here root 1 minus a. When we do that, we should get our common denominator. The numerator of the first top left fraction should now be 4 root 1 minus a. And then I will subtract from it the other one, which will be 4 root 1 minus x, all over the common denominator. That's these two are common now. So root 1 minus a times root 1 minus x. Then all of that divided by x minus a. What a mess this looks like. Okay, I don't see anything that cancels right away again. So in other words, I don't see anything that's going to cancel this out, so we don't have division by 0. So what I'm going to do is, because I see square roots, I'm coming in with conjugate. Top and bottom here, conjugate. Conjugate of what? Conjugate of this. So I'm going to go 4 root 1 minus a plus 4 root 1 minus x. And then 4, same thing, root 1 minus a plus 4 root 1 minus x. When I multiply the top together, okay, when I multiply these two, I do my FOIL up here. I get limit, let's see, x approaches a. I get the 4 times 4 is 16. The roots cancel, so I'm just left with 1 minus a, but that 16 will have to distribute to both terms. The middle terms will go away, and then I have the last two terms. So I get negative 16, and then again, the roots cancel. I'm left with 1 minus x, but that 16 has to distribute. All over this really, really nasty denominator, it's this times this. So I recommend that you just write that out. Don't try and multiply it out. Just write it out, because eventually that's just going to be sitting there. It's not going to cancel. So 1 minus a times root 1 minus x times, in parentheses, 4 root 1 minus a plus 4 root 1 minus x, and all of that over x minus a. All right, look at that numerator for a second, this here. Let's just multiply some stuff out here. This is 16 minus 16a minus 16 plus x, or plus 16x. The 16's cancel, and what you're left with is 16x. So this turns into 16x minus 16a. Factor out a 16, you're left with 16 times x minus a. That means that when we look at the denominator as a fraction and bring it up and flip it up here, okay, so that'll be gone. Then this top part, right, I know this is a mess, which is now 16 times x minus a, this and this will cancel. And so you're just left with that 16 on top and then that big ugly thing on the bottom. How great is that? Limit x approaches a. Let's see, we had the 16 on top that didn't go away. And all this junk down here, square root 1 minus a times square root 1 minus x times 4 square root 1 minus a plus 4 square root 1 minus x. And now I'm ready to try and let x become a. If x becomes a, this will become an a, and this will become an a. So trying to do this without going to a new page. No more limit. We have 16 on top, nothing changed. We have root 1 minus a, root 1 minus a again, 4 times root 1 minus a plus 4 root 1 minus a again, because x is a, right? This equals 16 over, all right, the first two terms here are the same thing. They multiply together, the root goes away, so I just get 1 minus a in parentheses. And then here, these two add together get 8 of them. So 8 root 1 minus a. And that should do it. That is the derivative. That equals f prime a. Very, very nice. All right, that's it for examples. I think I've shown you a good mixture of, the different algebraic manipulations that have to be done in order to figure out these slopes and, as we can see here, the derivative. All right, let's talk about two very important concepts. Let's say you have an object, say a box here or something, and it's moving in a straight line. So what we call this linear motion. Linear motion. Then what we can do if it's moving is we can talk about two things. First of all, its velocity, speed, and its acceleration. And if we graph this, in other words, we talk about, let's say we start measuring time, and then let's talk about the distance it travels. So at some point in time, this box is here, and then maybe another point in time it's here, and it's moving along. So at every point in time, right, this is t equals something. Another point in time here, t equals something else. And in different times, it's at different places. If I graph that, let's say at the first point in time, let's say it's here, and then later on it's here, and then later on it's, let's say, here. If we connect all those dots together for every point in time, maybe we get some sort of curve like this. And I don't know what it does. It does something like that. Okay. Then what we have is a distance versus time curve, and this right here is a function which we will represent by s of t. We will call it its position function. What it is it's a function that tells us where this box or car or bullet, whatever it is at every point in time. All right, so that's the s function here. Then if we look at the slope of the tangent line at some point, that slope of tangent line will give us our instantaneous velocity. It'll give us the velocity of that object at that point in time. So what we would need to find the slope of that tangent line is we would need to find the derivative of this at that point in time. Let's call that point in time A. So what we have is this, the velocity at t equals A. We're using t instead of x here because t is a better variable for time. The velocity at t equals A is the derivative of s at A. And this gives us what we call the velocity at A. Okay, so we'll call it v of A. This is very important. Now, since v of A, right, is velocity, turns out that if we take the derivative of the v function, we get acceleration, the acceleration of the object. The acceleration at t equals A is the derivative, the derivative of the velocity. And we'll call that A of A, even though A of A is kind of weird. But A here being acceleration, A here being the point. So this is a very, very important result in this class. If we have linear motion, something moving, and we know where it is at every point in time, right? If something moving, we know everywhere it is at every point in time. Then we can also tell anybody the speed it is at any point in time by just finding the slope of the tangent line or the derivative. And then we can also take derivative again and find the acceleration at any point in time. So let's take a look at an example. I'm looking at number 12 out of this section. It says, let's say that h is equal to 58t minus 0.83 t squared. Okay, let me just pop this book open real quick to make sure I state what this problem is saying. This is number 12. An arrow is shot upward with a velocity of 58 meters per second. Its height in meters after t seconds is given by this equation. So here t is seconds. T is measured in seconds. And h here, the height, is measured in meters. And we had an arrow, here's the ground, we had an arrow that was shot up, goes up and then starts coming back down. So this is linear motion, straight up, straight down. So let's just ask ourselves real quick. At t equals 0, what's happening? At t equals 0, you plug 0 in here, you get 0. So that means the arrow is on the ground. At t equals 1, where is this thing? Well, you get 58 times 1, which is 58, and then you subtract, let's see, 1 here, 0.83 times 1 is 0.83. So 1 second later, you're at 58 minus 0.83, so you're a little less than 58 meters high. So let's say if this is 58, we're a little bit less than it after 1 second. And then for every second, we could try different points in time, and then we could figure out, where it is. That's the basic idea. But let's talk about the questions here. First, find the velocity at 1 second. So how fast is this thing going after 1 second? B, what's the velocity at t equals a? So at any point in time, what's the velocity? C, when will it hit the ground? And then last thing, D, what is velocity when it hits ground? So this thing goes up, right? And we want to know first of all, how fast is it going 1 second after it shot up into the air? Then we want to know how fast is it going at any point in time. Then we want to know how long is it going to take to hit the ground, and then at what speed it hits the ground with. So overall, what we're going to need to know is the velocity of this thing, right? We need to know its velocity at 1 second and at t equals a seconds, and we also want to know what the velocity is when it hits the ground. So let's determine what the velocity is. Well, the velocity, velocity at any point in time should be equal to the derivative of this thing. Well, right now it's called h. So I'm going to call it h of t. And I'm going to say the velocity is the derivative of that. So what I want is, I want the derivative of that h function, or the slope of the tangent line, at some arbitrary point t equals a. So at this point, what I can do is I can take my derivative. Now, I'm going to use either definition, but I think I'll go with this one. Limit, I'm going to go with the other one. H approaches 0. Now, the derivative of h at a is going to be h of a plus h minus h of a. So I'm just using h instead of f. And then all over h. All right, this is limit h approaches 0. Okay, what we need to do is plug in a plus h into our function. So remember, our function is up here. Plug a plus h into this. So we should get 58 times a plus h minus 0.83 times a plus h squared, then minus, what is f of a? Well, f of a is 58a minus 0.83 a squared. Then all of that divided by h. Now, I'm going to save you some time, I'm gonna just write down what all that is. You have to multiply this out, distribute. You'd have to expand that, then distribute, and then distribute the negative through here. If you do all that, you'll get 58. Well, you distribute it and then you cancel things. Okay, so things will cancel out, and this is what you'll be left with. I'm not going to show what cancels. Minus 1.66AH minus 0.83H squared, all of this over H. So that's what you'll get. Notice everything here has an H, so I can cancel H. I could factor it out, but I'm just going to cancel, and then one of these goes away, so you'll have just a single H there. So at this point, you have limit H approaches 0 of 58 minus 1.66A minus 0.83H all over 1. So actually, I don't need to write it as a fraction, so because that H cancels. And now what I'll do is I'll let H go to 0. When I do that, this term will vanish because it has an H there. And all you're left with is 58 minus 1.66A. This is the slope of the tangent line, but now that we're talking about a linear motion, that represents the speed, right? This is the velocity of this thing at t equals a. So let's answer part A, okay? Part A, what was the speed of this thing at t equals 1? Well, the speed will be 58 minus 1.66 times 1 is just that. So you get 56.34. And since the speed, just like we normally use like miles per hour, this was meters per second. So the speed of the arrow was 56.34 meters per second. That's part A. Part B says, what's the speed of the arrow at A? Well, we just found that. The speed of the arrow, V, velocity of the arrow at A, is that derivative, or in other words, that slope of the tangent line. That's our powerful formula that we found. Okay, part C says, when will this thing hit the ground? Well, that requires no calculus at all, because if our position was given by this, I forgot the T there. This is the position of the arrow. Then we want to know when the height of this is 0, right? That's when it hits the ground, when the height's 0. And this is an equation. It's actually quadratic, but I can just factor out a t on the right side. Set that equal to 0. I'll just move the 0 to the other side like that. And now that I have two things that multiply to 0, I set them each equal to 0. Of course, this says t equals 0. So I know that the height of the arrow is 0 at the beginning, t equals 0. And then when I take this and I solve that, basically take 58 minus 0.83 t, set it equal to 0. Move things around, divide, blah, 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 you get t equals 69.88. That does not seem right, but it is. Okay, 69.88 seconds. Doesn't seem like that arrow could be in the air that long, but hey, this is a word problem. It's made up. Okay, and then finally, part D is what's the velocity when it hits the ground? So what we need to do to find the velocity when it hits ground is take our velocity, v of a, which we said was 58 minus 1.66a, and we need to replace a with 69.88. When we do that, we get 58 minus 1.66 times 69.88. You should get about negative 58 meters per second. All right, that's it. So I hope that makes sense. The main idea here, again, going back to all this, is that, again, if you have a position function, the derivative of it is velocity. So we're going to need and then you take derivative again, you get acceleration, although that problem we didn't deal with that. Okay, we're going to get into 2.2 now. And this is the derivative as a function. And it's going to be a little bit of a break time for me now. Okay, let me pick up here where we left off. Derivative as a function. So what we've seen so far is that if we're given some function of x, okay, that we can talk about the derivative there, slope of the tangent line, at a specific point, let's say like at 2. Or we could also say, what's the derivative or slope of tangent line at some arbitrary point a? Well, we've used a as our variable to let us know that what we mean is that we're going to let x be some arbitrary number a. But since a is just a letter, we could, if we want, say, what is the slope of the tangent line at, let's say, x? So all we're doing here is using the variable x instead of a. So this right here represents the slope of the tangent line to this function f of x at the point x. So draw a graph. Here's our function f. Pick some arbitrary point. We call it x instead. And then this gives us the slope there. Now, what we can see is that no matter what x we pick, we always have some numerical answer. We have some slope, okay? So what this leads us to is the fact that if we start with a function and you talk about its tangent line or slope of its tangent line at every point, it gives us a new function. So we start with the function of x, and we come up with a new function called its derivative. And so the process of taking a function f and turning it into its derivative is called differentiation. So what we can do is we can take the old formula we had where we said limit h goes to 0 of f of a plus h minus f of a all over h. Here we were saying, all right, we're going to let x equal a, and that was our definition for the derivative or slope of tangent line at a. Now what we're going to do instead is we're just going to replace those a's with x's. So we have the derivative of the function f at x is equal to the limit h approaches 0, f of x plus h minus f of x all over h. And this is something you should probably put into your memory bank as the definition of the derivative. This is the derivative of f, is that limit. Now, because this is used so much and it's so important, we have different notations. So here, let me give you some of the notation that we have here. The notation is, let's say, if y is given to us as being some function of x, then the derivative, f prime of x, can also be written as y with the little mark here. We call that y prime. Or we could also call it dy dx. And there's other notations that come later as you go on, take more calculus. There's this one here. This means the derivative with respect to x, meaning x is our variable, of the function f of x. So those are just different notations that we should be aware of. The ones that we'll be using most of the time in this class are those three right there. Okay, now let's take a look at a couple of functions and just the graphs and talk about the slopes of tangent lines and what its derivative or the derivative function would look like. So we'll start out with something basic. Let's say we have a graph that looks like this. Let's say up here it's 1, up here it's -1, and let's say the function does this. It comes this way, straight, flat line there, and it goes this way like this. Okay, and then let's put a dot there, put an open circle here. So this is our function f. Let's talk about what its derivative is. So let's just pick some arbitrary point x, go up to the function, and talk about the tangent line here. Well, the tangent line is flat. It's horizontal. That means it has a slope of 0. So what we know is that the derivative at that particular point would be 0 at that particular point. Now, if we go to another point, pick something, and again, the slope is 0. In fact, any point that we pick over here, the slope will always be 0. So it looks like the derivative of this function is always 0. Now, if we pick some points back here, like pick an x here, go here, and we get a flat line again, a flat line here, no matter what we pick to the left over here. So again, it looks like this is going to be true all the time. The only problem that we have here is that something is happening at 0. We have this jump, this break in the graph. So the question would be, what's the derivative of this function at 0? Well, it turns out that in order for your derivative to exist, all right, you cannot have a break in the graph, all right? So here we have a break in the graph, therefore the derivative won't exist. We'll talk more about this later. I just really wanted you to see how these slopes were 0. So it looks like this derivative is going to be 0 whenever x is bigger than 0, and whenever x is less than 0, we know that our derivative is 0. Okay, let's take a look at another graph. Say we have something like this. So we have a graph that goes up and then comes back down. And let's just split it right here. Let's just say that that's the number 2. Okay, here's 1. So looks like if we're anywhere on the left side of 2, any of these points over here, our slope is always the same. In fact, since these go up as you move from left to right, we could say that our derivative here is actually positive, greater than 0, because slope of tangent line is positive, right? That means greater than 0. Here we go look at points to the right, look at our tangent lines there, we notice that they're negative slopes, right? They're pointing down as we move from left to right. So there, our derivative is negative. So again, what would be happening here at 2 is a question. Again, we'll address that later because, you know, what's happening at this weird corner point. So let's get to that later. But for now, let's just recognize that to the left of 2 over here, and to the left of 2, our derivative is positive. To the right of 2, our derivative is negative. So some other things to look at. What if you have function looks like this? Straight line. Well, here, our derivative, take any point. Slope here is constant. It's always the same. Therefore, our derivative is going to be positive because it's pointing up as we move from left to right. But it's always going to be constant. It's always the same number. So I don't know what it is because I don't know the slope of that line, but I can tell you that it's a constant. So what we're trying to get at here is just making sure we understand the connection between a function and its derivative and how they're connected to each other. Let's now talk about you know, when a function would not be differentiable, when the derivative doesn't exist. So we have some graphs that we want to look at. We've seen that before. We haven't seen this. This is called a cusp. And these are different graphs I'm drawing here. Okay, so I want us to look at the points that I have on this graph. All right, don't worry about what's happening, you know, here, because, you know, at those, whenever you're on that part of the graph, the yellow part, our derivative is pretty well defined. We have slopes of tangent lines, right? Anywhere we go in that yellow, we've got slopes of tangent lines. So our derivative exists. It's those points that we have to be concerned about. So look at this one over here. Look at your slope of your tangent line here. That looks like it would be vertical. And remember, vertical lines have undefined slopes. So that becomes a problem. So If we have a corner, if we have a cusp, right? This case right here, our derivative is infinite. In other words, infinite slope. Okay. Or if we have a break in our graph, okay, our graph does something and then breaks off like this. If we have a jump, in any of these cases, our function is not going to be differentiable at that point. So at all these points here, our derivative doesn't exist. So keep that in mind if you ever have a graph that looks like any of these and you're trying to figure out, what's slope tangent line there or what's derivative there, it's not going to exist. And that just means that the limit, you cannot take that limit. The limit will not exist when you try and evaluate it. Now, we also have a theorem, though, that is somewhat related to this. It says if your function is differentiable, which means if you can take its derivative, if that limit exists, if differentiable, then f must be continuous. And remember, continuous means that you can draw it without picking up your pencil. So be careful in the order in which this is stating things. It's basically saying is that if you have a slope of a tangent line on the graph somewhere, then that graph has to be continuous at that point. It is not the other way around. So a lot of people make mistakes, and they think that this theorem can be read from right to left. So let me give you an example. This cusp, right? That's a continuous function because you can draw it without picking up your pencil. However, at this point, we're not differentiable. So just because you're continuous does not mean that you have to be differentiable. But if you're differentiable everywhere, so let's say you have a graph that looks like this, everywhere you go, you have a nice derivative. It's defined. Slope of tangent line is defined everywhere. If it's differentiable everywhere, then it must be continuous there. So that's the theorem. Keep it in mind. Now, since we have this idea that you can start with a function, and from that function you can take its derivative and create a new function, well, what stops us from doing another derivative of that function? Well, we can, and it's called the second derivative, and we use a double prime mark there, double prime. And we could also go 3. So you could take the derivative of that, and you can keep going forever. So let's see, what would come next? 4? Well, we kind of run out of prime marks. So what we do instead, okay, what we do instead of the primes is we just write a little 4 in parentheses. And that lets everyone know that what we're doing is we're taking the derivative 4 times. And then we could do 5. And then, of course, as many as you want, you could do n derivatives. So this notation here means you're taking the nth derivative. Now, do not confuse that. Do not confuse f with the little 5 there of x. Do not confuse that with this. These are totally different things. This means take the function f and take its derivative 5 times. The other one means take the function f and raise it to the 5th power. So this is like an exponent raising to the 5th. This one is 5th derivative. That's why we put it in parentheses. That way you can see it. So, all right. Now, using that notation, I want to go back to something that we had earlier. We said earlier that if you had a function that was distance versus time, position function, s of t, we said that the velocity was the derivative of s. So we have that. And we said that the acceleration was the derivative of the velocity. Well, if you're looking at the derivative of velocity, and velocity is a derivative of s, then you could really say acceleration is the second derivative of the position function. So all of these are kind of connected to each other. All right, start with the position function, take its derivative, you get its velocity. Take its second derivative, you get its acceleration. Now that was for linear motion, remember. All right. What we're going to do now is we're going to try and do a little practicing of sketching what derivative functions look like. So let's say we have a function. I'm going to make one up here. I'll draw it in red. Let's say it does this. Let's say that it goes up, and then it goes across, and then it goes down, and then back up like that. All right. So this is f. What would its derivative look like? So I'm going to start with the easy points. Let's start at 0, and I'm going to do the derivative in red. If I go up at 0 and I look at the slope of the tangent line, the slope is 0. So what I can say is that the derivative of f at 0 is 0. Right? Now, what I need to do is I need to plot this like an ordered pair. At 0, I get 0. All right? And this is my derivative function that I'm about to graph. So I'm going to put a green dot here. At 0, I'm at 0. So now let's pick another point. Let's go out here, let's say about right there. If I go up, what's the slope of tangent line there? Well, let me just call this point, I'll just say it's 1, just so it's easy. I know the derivative at 1 was 0. That means I can look at that as an ordered pair. Again, at 1, I should be 0. That's what the derivative looks like. So at 1, I should be at 0. In fact, if I would have picked any points in here and would have looked at the slope of the tangent line up here at top, it would have been 0, which means that my function, my green one, my derivative, should be 0 all along here. And it should stay 0 all the way until I get to here. All right, so it should stay 0 all the way to there. Now, once I get past that, well, you know what? Let's go back to the left. Notice that if I pick any of these points, or actually any of these points, and look up, all my tangent lines are 0. So I would have 0 for my derivative function all the way until I get to here. Now, let's pick something over here. Let's say we pick this point. We come up here. It has a slope. I'm not sure what it is, but it's some positive number, which means that, and since I can't tell what that slope is, it looks like it's about 1. Let's just say I go up 1 here. That's what my derivative looks like there. And if I go to this point here and go up, my slope is also 1. So it's like that. If I go here, my slope up here is also 1. So it looks like that. And it looks like that all the way over here until, well, the graph ends, so I'm just going to stop it there. So it looks like that. Now, on the other side, come pick a point, come up here, take a slope. Looks like it's -1. So what I'm going to do is go down 1, plot -1. If I pick a point here, come up here, slope of tangent line, that looks like it's about -1 also. And then over here, it looks about -1. So it looks like it stays -1 all the way over here until I get to here. Now what happens is, as I get closer and closer to this bottom point, it looks like that slope's becoming less steep, which means that it's less negative. So what happens is this down here starts to come up until I get to this point right here where it's actually bottomed out, and here my slope is 0, which means that my green graph needs to cross through 0. And then as I move to the right, anywhere over here, my slopes are starting to become positive, which means my green graph needs to be positive. And it looks like they're starting to get steeper and steeper, so bigger and bigger values. So I hope this all makes sense, but the derivative here, the derivative is graphed in green. So you can see that starting with the original function, we know that we can take its derivative and create a new function. That new function has a graph, and this is the graph of it. So the challenge will be for you to try some of your homework problems to start with the picture and just look at it, what its derivative would look like. Now there's some things happening here. We're going to leave these open circles here so that we know nothing's going on at those points. There's just jumps in the graph. All right, getting to some problems here. Let's take a look at more computational stuff. And I think right now I'm going to take a quick little break. Okay, back to work here. So we're going to do a couple of examples now that we've got most of that graphical stuff out of the way. Let's take a look at a problem like this. F of x equals x squared minus 1 over 2x minus 3. All right, we are tasked in this problem finding the derivative. All right, so we've done this before. The only difference here is that we have an x there instead of an a. So we're going to use the definition that the derivative of a function f at x is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. So as before, what we did was we plugged, earlier we plugged a plus h in. Now what we're going to be doing is plugging in x plus h. So we're going to be replacing x with x plus h. We have to be very careful when we do this because a lot of people kind of just like to throw an h out here at the end, say, oh, that's what it means to plug in x plus h. But remember, the entire x here gets replaced with this instead. So I'm going to write this out. I'm going to actually do this like scratch work. What is f of x plus h in this problem? Well, it's x squared, but I'm going to be doing x plus h instead. Then minus 1 all over, and then the bottom is 2 times x, but I'm going to replace that x with x plus h, then minus 3. All right, and now I'm going to have to figure out what, minus f of x is. Well, f of x, of course, is just the function itself. I don't have to do anything to it. So I'm just writing things down right now. I'm not actually putting it all together. And then I'm going to divide that all by h. So here we go. The derivative of f at x is equal to the limit as h approaches 0 of this ugly thing, x plus h squared minus 1 over 2 times the quantity x plus h minus 3. Then subtract from that f of x, which is x squared minus 1 over, over 2x minus 3. Then divide all of this by h. Now, if you let h go to 0 right now, you're going to get 0 over 0, which means that we have to do some algebra before we can do any of this. So this will equal, all right, limit h goes to 0. All right, the numerator is a complex fraction. So we've already seen with complex fractions, what we need to do is we need to insert things top and bottom here, so that we get common denominators. Well, the common denominator I'm going to need is going to be this guy next to this guy. So I'll have to put this one here and here, and I'll have to put, let me use this one here and here. And that's what I'm going to write on my next line. All right, so big mess. I have my 2x minus 3 on the top and bottom. 2x minus 3 times, now the top left here was that x plus h squared minus 1 over, now the bottom was 2 times x plus h minus 3. And then we had minus, then I had my x squared minus 1, my 2x minus 3. And now I'm going to come in here and put that other denominator, which was this one. I'm going to put that right here and here. So I'm going to put 2x plus h minus 3 over 2x plus h minus 3. Now, all of this is divided by h. All right, fun stuff, right? So what we need to do now is multiply this here, put all that together, and then multiply this here. So in this multiplication, it might be worth it for us to first try and simplify what this is before we multiply that through. So let me go ahead and write out the limit. H approaches 0. It's going to be a lot of writing here. 2x minus 3. Then we have all that stuff becomes x squared plus 2xh plus h squared, and then minus 1. So I expanded this out, and then I had the minus 1 there. Or I expanded out, multiplied it times itself, collected like terms. And then that's all over my common denominator, which was the 2x minus 3 times the 2 times x plus h minus 3. then minus over here, I had the x squared minus 1 over the 2x minus 3. Now let me go ahead and figure out what this was. This was 2x plus 2h minus 3, and this was 2x plus 2h minus 3. And then all of that over h. So what we need now is to multiply that out. And that's just an algebraic exercise, which you would do just so to remind you, you'd go here times this times this times this, and then you'd go this times this times this times this. Collect all your like terms together, then this times this times this, then this times this times this, and you put all that together. So to spare us the work of seeing all that multiplied out, I'm just going to write out what that would become. We should have a 2x cubed plus 4x squared h plus 2xh squared minus 2x minus 3x squared minus 6xh minus 3h squared plus 3, and then minus, here's where that minus came in. So I'm at this point right here. Minus, I'm going to probably run out of room here. In parentheses, I'm going to put it all in parentheses because I have to subtract it all. So I'm actually doing this part of this right now when I multiply all that out. That would give me 2x cubed plus 2x squared h minus 3x squared minus 2x. I'm getting smaller here as I'm running out of room. Minus 2h, and then plus 3. All right. All of that over the common denominator, which would be, this is the common denominator in both, so I'm just going to write that below this. 2x minus 3 times 2 times x plus h minus 3, then all of that divided by h. My goodness. This is what makes calculus so challenging, is all this algebra. All right, so when we start to put this all together, things start to cancel. This 2x cubed, this 2x cubed. Let's see, what else cancels here? We've got a negative 3x squared, negative 3x squared. We've got a negative 2x, and then this one, negative and negative becomes positive. The 3's at the ends cancel. And what else? I believe that's everything that cancels. What we should be left with is limit h goes to 0 of, let's see, 2x squared h plus 2xh squared minus 6xh minus 3h squared plus 2h all over our common denominator. Our common denominator was 2x plus 2h minus 3 times 2x minus 3. That's just all I did here was distributed that through. So that's why it looks like this right here. And I switched the order of them, no big deal. All of this divided by h. What you'll notice now is that every term in the numerator has an h in it, so you can factor an h out, and then they cancel out with the one on the bottom. So you'll get limit h approaches 0 of, oh my goodness, I apologize, I've got the Spurs game on in the background. I'm getting distracted. So when we cancel an h, we get 2x squared plus 2xh minus 6x minus 3h plus 2 all over our common denominator, 2x plus 2h minus 3, and then 2x minus 3 here. So the h went away on the bottom. And now finally we can let h go to 0. So when we let h go to 0, certain terms will vanish. This term's gone, this term's gone, this term is gone. And so what we're left with is 2x squared minus 6x plus 2 over 2x minus 3. That's 2x minus 3, and then another 2x minus 3, so squared. Whew, okay, there we go. All that work. This is the new function that you get when you take the derivative of that original function. A lot of work there. Lots and lots of works. That's the extent of 2.2. We're going to move into 2.3 next, but I'm going to take another quick break. Sorry. Okay, the homework for 2.2 is going to be a lot of algebra, a lot of what you've seen me demonstrate, like in the previous problem. But you know, it's kind of like the torture session of Cal 1. 2.3 is where we finally get to a place where we can get some shortcuts and not have to do that big long limit that we've been working with. This section is about the differentiation formulas. We love formulas. All right, so let's go through these. All right, there's going to be a couple of them. So the first formula for taking derivatives is this one. And I'm going to use a different notation. It says if you're going to take the derivative, so this is using an alternate notation here. Oh, I'm getting a call. Gosh, I apologize. All right, so this notation means I'm going to try and take the derivative, okay, the derivative with respect to x, meaning that x is my variable. And here's what I would like to take the derivative of, a constant, c. Well, let's think about that for a second. If you have a function that's constant, that means it's just flat line, it's always some value c, then the slope of the tangent line at any point, right, pick any point, the slope is always 0. It's flat. So the derivative of a constant is always 0. Okay, so that's a formula. It makes sense. Visually, it makes sense. But how can we show that with the limit? Okay, so let me show you. Let's start with a function that is constant. All right, and now let's try and find its derivative. The derivative would be the limit as h approaches 0 of f of x plus h minus f of x all over h. But the limit as h goes to 0, what is the function's value at x plus h? Well, it doesn't matter because that function spits out c all the time, minus the function's value at x, but that doesn't matter because it always spits out c, all divided by h. And now what we get is c minus c is 0. Now, we're not saying it's approaching 0, we're saying it is 0, and therefore the limit as h approaches 0 of 0 over some very small number, this will be 0. Very important that you understand that before, when we were saying 0 over 0, we were saying the top was approaching 0 and the bottom was approaching 0. Here we're saying the top is 0, and 0 divided by any number other than 0 is 0. So we get 0. So that matches with what we got visually. Okay, next formula. 2. What is the derivative, treating x as our variable, of the function x itself? Well, again, let's take a look at a graph. The function x is the identity. It's the perfect diagonal line. And if we go to any point on this line and we look at the slope is always 1, right? Rise over run, up 1 over 1. So the answer to this should be 1, which it is. Now, how can we show that? Again, the derivative will be the limit as h goes to 0 of f of x plus h minus f of x all over h. Now keep in mind the function we're actually using here is the function f of x equals x. So whatever you plug in is what exactly comes out. So this top left corner, when I say what do I get when I plug x plus h in? Well, it should spit out x plus h. So this is limit h goes to 0 of x plus h, and then minus, what do I get when I plug in x? Well, it spits out x, and then all over h. The x's cancel, and you get h divided by h. H divided by h is 1. So limit as h goes to 0 of 1 equals 1, and that's because in this expression 1, h doesn't appear, therefore h doesn't make anything vanish, so you just get 1. And again, that matches up with what we got earlier. So I'm trying to show you this is the formula. The derivative of x is 1, but we can show why it's true by using the limit, proving it. All right, the next formula is a very powerful formula. It's called the power rule. It says, what is the derivative with respect to x of not just x, but x raised to some power, n? And the answer is n times x raised to the n minus 1. So what I want you to see happens here is that when you have x to a power and you want to take its derivative, the power comes out front. The x remains as the base, and then the exponent is now that power you had before, but take 1 away from it. Now, I'm going to think about whether or not I want to show you why this is true. Let me first show you some examples of this, and then I'll decide if I want to show you why it's true. So here's an example of this. Let's say you have f of x is x squared, and you're asked to find f prime of x, the derivative. Well, since we have x being raised to some power n, we can apply this formula. So the derivative should be the 2 comes out front, then I have x, and then I subtract 1 from 2, so 2 minus 1. Well, this is just 2x to the first power, but we usually don't write the first power, so this is just 2x. So the derivative of x squared should just be 2x. Another example. Let's say we have f of x equals x to the 237th power. Well, again, we have a base x. We have our exponent is this number 237. That's our n. So by this power rule, it should just be the 237 out front. X raised to the 237 minus 1 is going to be 236. And that is it. We're done. Very nice, very short, very quick, very easy. Next one. Let's say we have f of x. This sure beats the limit, doesn't it, doing all that stuff? How about we have square root of x? All right, well, first thing we have to do is realize that square root of x is really x to the 1/2. So if I look at that, I have a base, x, and I have a power, which is my n, which is 1/2. So the derivative should be that 1/2 coming out front, then my x raised to 1/2, take away 1. But 1/2 minus 1 is negative 1/2. And remember with negative exponents, we don't like to leave things with negative exponents usually, but you can. It's not wrong, but we like to rewrite it. So rewriting that as a positive exponent means it needs to be pushed to the bottom. So we'd have 1/2 times 1 over x to the positive 1/2. But that's the same as 1 over 2 times 1 over the square root of x, which is the same as 1 over 2 root x. And that's the way you should remember it. This one comes up a lot, so you should just probably put this into your memory bank. The derivative of the square root of x is 1 over 2 root x. Remember that one. Let's see, we could try something else. How about f of x equals, let's say, 1 over the 5th root of x. So let's try and find the derivative. Well, we first need to realize this is 1 over x to the 1/5. And then, before I use power rule, I need to bring that up and rewrite it as x to negative 1/5. That way I have a base, and then I have an exponent that is a number. So the derivative should be, that number should be dropped out front, negative 1/5, x to the negative 1/5 minus 1. So this is negative 1/5, and then when you subtract 1 from negative 1/5, you get negative 6/5. And then, again, dropping that down, negative 1/5 times 1 over x to the 6/5, which is negative 1 over 5 x to the 6/5. And that will work. Okay, let's take a look at another example here. I think I've shown enough here maybe. Let's just try one more. How about f of x equals 1 over x? All right, same thing. Bring x up, re-rise x to negative 1. Now take derivative. Power comes out front, negative 1. Subtract 1 from the power. 1 minus 1 is negative 2. Drop that down. When I drop it down, I'll put the negative on top. It'll become x squared on the bottom. Okay, so now we're kind of seeing how this is going to work. I think what I will do is I will defer. I will not show you the proof of the power rule at this point in time, because I think you've got enough on your plate to work with. So if you're interested in that, please just contact me. I'd be happy to show it to you. All right, so how about one more rule that we can take a look at before we finish this up. Let's see, that's our second rule. And we had our third rule is the power rule, so fourth rule. Okay, fourth rule says that if you are trying to take the derivative of a constant, now we already know the derivative of a constant by itself is 0, but if it's a constant times a function, okay, this rule says that what you can do is you can pull the constant out front and then just take the derivative of the function. So you don't have to worry about the constant. The constant will just come out. Let me show you an example of this. Let's say we have some function, f of x equals 4x to the 5th. So what we want to do is we want to look at this 4 out here in front as being like our constant. And then we have a function, f of x, which is the x to the 5th. Now we know how to take derivative of x to the 5th because that's power rule. So what I'm going to do is I'm going to say that the derivative of this is equal to 4 times the derivative. Well, I'm going to use a different notation so you can see it. It's 4 times that x to the 5th, but it's derivative. So I'm just going to put a little prime mark on that parentheses. That just tells you, okay, I need to take derivative of that still. But the derivative of x to the 5th is 5x to the 4th. And now that 5 and 4 multiply together, it gives you 20x to the 4th. So the constant will come out. It'll just multiply whatever's out there. So nice result. I think that's good. Trying to wrap up a couple of things here. How about something like this? What if we have, as an example, what if we have, I'll use y instead. What if we have y is equal to x squared minus x plus 2 over x? Okay, what's the derivative of this? So what is that? What's y prime? Well, you might be sitting here going, well, wait a minute, we haven't done this before. We have a fraction here. Well, we do, but because we have a single term in the denominator, we can split this up into 3 fractions. We can go x squared over x minus x over x plus 2 over x. And then simplifying, we get x minus 1 plus 2 times x to the negative 1. So I simplified these two, right? I simplified these two, and then that last one, I brought the x up top and made it a -1 as an exponent. All right, so now what we can do is we can take the derivative of each of these individually because they're separated by addition and subtraction. So my derivative will be the derivative of x, which we said earlier was 1, okay, plus the derivative of a constant. Derivative of constant is 0, plus, now here we have a constant in front of a function, right? We have a constant here in front of a function, so I'm just going to write the constant. And now the derivative of x to the -1, the -1 comes down. I subtract 1 from the exponent. So what's left here is 1 plus, well, actually it'll be a minus because I'm going to multiply 2 times -1. So minus 2, and then x to the -2 can go down on the bottom as an x squared. There it is. All right. Good, good, good. Making a little bit of progress here. All right, let's now look at, we had a problem earlier where the arrow was shot into the air, and they gave us 58t minus 0.83t squared, and we went through and we tried to find its derivative, slope of its tangent line, and we went and did a lot of work for that. But let's just see how quick and easy this is now. If we want this derivative, we have two terms because they're separated by addition or subtraction. So I just need to take derivative of each one of these individually. Well, the 58 sitting in front is a constant in front of t. Now t here by itself, if I take derivative of t, that's like me saying what's the derivative of x? Derivative of x is 1. Okay, or derivative of t in this case is 1, because t is our variable, so just understand that. You know, we're interchanging the x that we normally had with the t now. So over here we have another constant, 0.83, attached to a function. The function is t squared. Derivative of t squared is 2t. And now what we can do is just write 58, and then multiplying negative 0.83 times 2, we get negative 1.66t. And that's what we worked like, 20 minutes for a while back. So very, very nice result here. The last two that I want to show you, I'll make quick, is the derivative of sine, the sine function, and the derivative of cosine. So derivative of sine of x is cosine x. And then next to it, the derivative of cosine x is sine x. These two need to go into your memory bank. These are very important. They come up a lot. And again, I believe I'm going to spare you the proof of these. You just kind of take them on faith for now, but please just go YouTube it. Just go look up, proof of derivative of sine or something like that, or derivative of cosine. It's a really nice proof. Again, if you want to see it, just contact me. Come, meet me in my office. I'll be happy to see it. I'm just really trying to cut down on some of the time on this video, so I'm not going to show you the proof of that. All right, that's going to wrap up those sections, and I guess you move on to the next videos. Sorry again that I had to redo this one. I don't like doing these at home like this, but it is what it is. You have at least something to go off of.